Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of organic chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we will be looking at Benzenediazonium salt chemistry. Benzenediazonium salts can be formed from the molecule aniline. If you recall, we can take benzene and react it with HNO3 and H2SO4 and when reacted with these reagents we can make nitrobenzene. Now if you take nitrobenzene and react it with tin, SN for tin, HCl, or you can use, instead of tin, you can actually use iron, HCl. Either of these reagents will do the same thing. We can convert our NO2 to an NH2. And we can make aniline. Aniline. Now, aniline is susceptible to attack by electrophiles. In fact, the lone pair on the NH2 is susceptible to electrophilic attack. And we can use sodium nitrite, NaNO2, in HCl from 0 to 5 degrees Celsius. Now, sodium nitrite and HCl will make nitrous acid, so you could use as a reagent, instead of sodium nitrite HCl, you could use HNO2, which is HONO. And we'll look at how that forms in a second. If you carry out this reaction, you will produce as your product nitrogen, triple bond, nitrogen, lone pair here, there's a plus on the middle nitrogen, and so because we have HCl we have a lot of Cl minus. Cl minus comes from the HCl. We produce the molecule Benzenediazonium Chloride. Probably don't have room to write it out, but I will try. I'm going to have to put a hyphen. It's all one word as in the title. Benzenediazonium. And then the separate word, chloride. Now that's quite a change from an NH2 group. One might ask, how do you get an N triple bond N out of an NH2? Well, as I've stated, it does involve an electrophilic attack. So clearly we're producing some kind of reactive electrophile from our sodium nitrite and HCl. So what we're going to do is look first at sodium nitrite reacted with HCl before we establish the mechanism of formation of Benzenediazonium chloride. Now sodium nitrite can react with HCl to produce sodium chloride, and HNO2, which is HONO, nitrous acid. So we have nitrous acid. We can then take the nitrous acid and react it with another HCl molecule. If we do, we can protonate the HO group, producing the good leaving group water. So this can readily fall apart, yielding water plus NO plus. Now you don't want to get NO plus mixed up with the electrophile produced by HNO3 and H2SO4. If you recall, HNO3 and H2SO4 produced NO2 plus. NO2 plus was called nitronium ion. NO plus is referred to as nitrosonium ion. And it has the Lewis structure where there's a plus on the oxygen. This is the electrophile. The nitrosonium ion is the electrophile that reacts with the aniline that gets us started in the formation of our Benzenediazonium chloride. So how does the Benzenediazonium chloride actually form from this molecule? Well, that reaction is as follows. First, note that nitrosonium ion has a minor resonance contributor, which can help us understand the nature of the reactivity. Nitrogen's electronegative, and if it withdraws the electrons, that is, the pi electrons form a lone pair on the oxygen, we get 6 electrons on nitrogen, a +1 formal charge. Because nitrogen lacks a filled octet, this is a minor contributor. This contributor allows us to understand how the molecule can react with aniline. If I draw NH2 with a lone pair, NH2 with a lone pair can react with my nitrosonium ion, positive charge on nitrogen, attracts the lone pair electrons. You might wonder why the electrophile does not attack the aromatic ring. Remember, disrupting aromaticity on the aromatic ring is higher energy than most alternative paths. Since NH2 does have a lone pair, it would go onto the NH2 first. In many molecules, such as phenol, such binding to a lone pair does not lead anywhere. However, in this case, with aniline, we're actually going to get a product. So, I'll put my H's up here. Now have a plus on this nitrogen, and we have this molecule. Okay, so very quickly we can deprotonate Now, in aqueous solvent, protons transfer all the time, especially if there's acid around and we have HCl. And so many of these lone pairs will get protonated and deprotonated. However, if you protonate the oxygen, so there's a plus on the oxygen, I can draw a resonance contributor for this. Where essentially this lone pair dumps in to create a pi bond, and these pi electrons go out on the oxygen to create a lone pair. And the positive charge is now shifted to the nitrogen. This can set up a deprotonation. Setting up that deprotonation as follows. There we go. And this lone pair and this nitrogen. Now we can reprotonate. Another proton adds to the OH. And I will produce the good leaving group, water. Very nice indeed. Water is a good leaving group. A loss of water leads to a minor contributor of the Benzenediazonium salt. Minor because the right-hand nitrogen has only 6 electrons around it. It has the positive charge. So resonance stabilization can dump in the pi electrons and generate our N triple bond N. Lone pair of nitrogen on the right and puts a positive charge on the middle nitrogen. Nitrogen on the middle of the molecule. And there's an associated Cl minus from the HCl, my Benzenediazonium Chloride. So there you have it. Electrophilic attack by the nitrosonium ion on the lone pair of nitrogen. We get a series of protonation, deprotonation steps, loss of water to generate our aromatic ring with an N triple bond N, Benzenediazonium Chloride. Now what's interesting about Benzenediazonium Chloride is that the material undergoes a series of reactions. The N triple bond N group is a very good leaving group because it produces nitrogen gas, which is extremely stable. It is such a good leaving group that above +5 degrees this molecule falls apart. Now one could envisage this N2 leaving, and if it left, and you lose N2 gas, it bubbles out of solution, one could envisage the formation of a benzene carbocation, which would have a sp squared orbital that's empty, where there's a plus charge on it. Now, such formation of a carbocation, because the empty orbital is sp squared, held closer to the nucleus, such benzene carbocations are even less stable than primary carbocations, and so would be extremely reactive and susceptible to attack by nucleophiles. In many cases, the mechanisms may involve radical processes and not these types of carbocations. But the driving force behind the loss of N2 gas is the huge amount of energy released, and the fact that we do not have to disrupt the aromatic ring to get reaction. So we're getting around the stabilization of the aromatic ring by having a very powerful leaving group on the ring. So what kind of reactions can Benzenediazonium chloride undergo? Well, I'm going to write Benzenediazonium chloride here in the middle. I'm going to just write it as N2 plus. And a Cl minus. One of the first reactions that we want to look at is reaction with hypophosphorous acid. We can take H3, PO2, at 0 to 25 degrees Celsius. And if we do that, we will make benzene. Now, first question that may be jumping into your head is, why on earth would one ever want to do this? I mean, after all, we took benzene, hit it with nitric acid to make nitrobenzene. We then hit it with tin HCl to make aniline. And then we hit aniline with the sodium nitrite HCl to make diazonium chloride. And then you just take it back to benzene. Have a 3-hour lab reforming your starting material? What's the point? Well, suppose I wanted to make this molecule. Metachloroanisole. Metachloroanisole. How could I begin to make a molecule like metachloroanisole when it's well known that both methoxy and chloro are orthopara directors? How could you place a chloro on the molecule? Well, the strategy involves putting a group on the ring that would generate the metachloro derivative and then allow us to remove that group so that you just have the meta arrangement as shown here. For example, suppose I have NH2. Well, actually, I can do this. I can start with benzene, and I can make my phenol derivative, or I can start with phenol. But let's start with, just to show the key point, para-aminoanisole. How could I have made this molecule? Well, I could have used tin HCl. On the paranitrile anisole. So I could have had O2N. And I could have made this material by reacting anisole with HNO3 H2SO4. If I had done that, I could have gotten to my aniline. Now, anisole, the OCH3 group of, or the methoxy group of anisole, is an orthopara director. So clearly here we would have had the ortho product as well. But I could have isolated the para product and produced, by tin HCl, the para-amino anisole derivative. Now, what's interesting with this molecule is I could carry out a third substitution. I could use Cl2 and AlCl3. Now you have to be careful with this reaction. There's a possibility that lone pair on aniline may react with the Lewis acid, and you may not get the reaction you want. You may have to throw a protecting group on the lone pair of NH2. However, we will this course keep things simple and just press on. Apply our third substitution rules. In the third substitution, when you have two activators directing to different positions on the ring, the strongest activator wins out. Aniline is an orthopara director. Well, we can't substitute for methoxy in the para position, so aniline is trying to substitute ortho. The methoxy group here is directing ortho to itself. So these two groups are competing. In essence, the stronger activator wins out, which in this case is aniline. Since aniline is the strongest activator, it will direct ortho. And so the chlorine will end up ortho to the NH2. The actual process of this reaction may require a protecting group on the lone pair. However, there's every chance that this reaction will work. Now, the point I want to make is now to get to our final product, all I have to do is get rid of the NH2. How do I do that? Well, if I want to go to my final product, I make the diazonium salt. I hit this with sodium nitrite, and then I hit it with HCl, 0 to 5 degrees Celsius. And that will put N2 plus on the ring with my methoxy and my chloro. And you can see where we're going with this. Now all we have to do is hit this with H3PO2, and we remove the N2. We hit this with H3PO2 at 0 to 25 degrees C. And the N2 is removed, and you have your meta-substituted chlorophyll. So it is possible to use the NH2 group of aniline as a director and then remove it. And that can be useful in reactions. So this top reaction is indeed very useful, although at first glance it might seem that it is not. So what we're going to do now is look at some other reactions. We have not seen a synthesis of the molecule phenol. It turns out if you use H3O plus H2O, so we use acid at 100 degrees C, we will take the diazonium chloride salt and produce the molecule phenol. Very useful reaction. We can also, even though we can do it with electrophilic attack, aromatic substitution, we can make the halobenzenes. If we use copper chloride and we do it 50 to 100 degrees C, 50 to 100 degrees C, we can also make chlorobenzene. It's sometimes been called the Sandmeyer reaction. We don't have to use copper chloride. We could do the same thing with copper bromide. We could use the same temperatures. And make bromobenzene. Bromobenzene. Let's draw that B. Okay. And if you hit this molecule with potassium iodide, Ki, potassium iodide, you can make iodobenzene. Potassium iodide. Copper cyanide. Let's go a little further. Copper cyanide mixed with potassium cyanide. Also run at 50 to 100 degrees. Will yield the molecule benzonitrile. Now, I am not sure whether I've given you that name before, but if I haven't, you are responsible for it. So let's write it down. Benzonitrile. Now, benzonitrile is really useful as a precursor. You can use it to convert to carboxylic acid. So if you hit it with H3O plus, you will make benzoic acid. But I'm going to go way over here if I can. If you hit it with 1 lithium aluminum hydride, often you have to react that in ether, some kind of ether, and then 2, you destroy the excess hydride with H2O. The hydride, the H minus, attacks the carbon and replaces the triple bond with CH's. And then the water, when it attacks, ends up replacing, let's give it a little more room here, ends up replacing the nitrogen pi bonds with hydrogens. So the H's on the carbon come from the aluminum hydride, the H's on the nitrogen come from the water, and we produce the molecule benzylamine. So benzonitrile is a good way to get to benzoic acid and benzylamine. Of course, the one molecule I am missing in all of this is fluorobenzene. We have not seen a way of making fluorobenzene yet. If I use HBF4, fluoroboric acid, the H will grab the Cl, and become HCl, and the BF4 will be a counter ion. So you'll just make instead of Benzenediazonium chloride, you'll form Benzenediazonium tetrafluoroborate. So we still have our N2+, and this time we have BF4- as the counter ion. So it's the same thing. If you heat this, you will get fluorobenzene. So you could go directly to this by doing a two-step process. 1, HBF4, and 2, heat. And then they don't even have to be the same process or separate. You could actually just throw in HBF4 and heat and go directly to fluorobenzene. So you can do a whole series of reactions in which the good leaving group N2, and in all these reactions N2 gas is given off, and you can put all kinds of substituents on the aromatic ring. So Benzenediazonium chloride is a very useful precursor to a wide range of aromatics, substituted aromatics. But the Benzenediazonium chloride also has another interesting feature. If I re-examine its resonance structures, I can draw the minor resonance contributor. And I notice the right-handmost nitrogen is electron deficient. It only has 6 electrons. And I grant you this is a minor contributor. But because it's electron deficient, it is an electrophile. Because it's an electrophile, it could attack a highly activated aromatic ring. If I react this molecule with an activated aromatic ring, perhaps like N-dimethylaminoazobenzene, the electrophile can attack ortho or para. Aniline is an ortho-para director. And I'm going to focus on one of the products only. And I will get substitution in the para position. That is, I will form this molecule. Now this is an azobenzene unit with an N-dimethylamino group on. So I have para N-dimethylamino azobenzene. The azo refers to the N double bond N. Azobenzene are two aromatics attached by an N double bond N. I could likewise hit this molecule with sodium hydroxide, phenol, at 0 degrees. Now this is probably step one. We probably have to protonate it afterwards because of the presence of the base. The base will deprotonate and make the phenoxide. So we would get again, you could get a mixture of ortho and para. Para would probably be major because of the bulkiness of the electrophile. Now initially we get O- because we're in base, so if we did a second step to add acid, you will get to the phenol. And this is para-hydroxyazobenzene. Now, these types of molecules are important. In many organic molecules, the type of radiation that is absorbed by the organic molecule is ultraviolet. And so these molecules appear white. But compounds that have extended conjugated double bonds lower the energy of separation between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, HOMO and LUMO. And as that energy drops, you start entering the visible blue region. And when light of the visible blues is absorbed, light that is reflected is in the other wavelengths. And hence, you may get materials that look red in color. As we extend the conjugation more and more and lower the energy gap, and we start absorbing in the red regions, we reflect the blues. And you can see how extended conjugation can lead to, if you like, can lead to color. Color in paints, color in dyes, color in our clothing. And molecules of this type are very important in that area. Some are used as indicators. For example, a compound called methyl orange looks like this. And it appears yellow in base. If we protonate it, that is, if we add a proton here, we can disrupt or partially disrupt the delocalization, changing the energy gap, causing a color change. And in acid, it appears red. So this type of chemistry can be used with indicators. The last molecule I'm going to deal with is a very large one, and I want you to be able to recognize it and just give it to you as an example of the extensive delocalization required to produce a blue color. What you see here is a molecule that is used as a blue dye. Now, in order to get the color blue, remember, we must be absorbing in the reds in order to reflect the blue color. And to absorb in the reds, we have to make the energy gap extremely small. And this will require extensive conjugation. So, in order to do this, I will need lots of pi bonds. The SO3 minus groups have pi bonds. The aromatic rings have pi bonds. The N double bond end have pi bonds. This is an extensively conjugated system. The energy gap is so small that red wavelength light is absorbed and blue wavelength light is reflected. And this is known as the dye called direct blue 2B. Well, that's it for Benzenediazonium Chloride. I'm Dr. Brian Lloyd. This is my Scribblecast, and I thank you for listening